Okay, welcome back to the online lecture. This is the last week of this semester, finally. Okay, and as you can see, now we have a different method, different technical methods to deliver this week's online lecture. Anyway, I hope you like it. Okay, so this week we will study chapter 39, and the title is More About Matter Waves. So remember that we have learned the matter waves in the previous chapter. So here we will continue to study it. Okay, let's begin by reviewing the last lecture. So there in the last lecture, so 38, okay, we learned that the photons behave as particles with quantized energies and linear momentum. That was the essentially important idea about quantum physics. And we also learned that electrons are matter waves. So we learned that electron was a particle, but now we learned that electrons are matter waves, which can be expressed by the de Broglie wavelengths. Okay, and in doing so, we learned that these matter waves are actually probability waves, and if you take the square of it, it becomes a probability density, which actually represents how this matter wave exists in space. Okay, and finally, we learned the famous Schrödinger equation, which is useful when you try to know what this matter wave look like. Okay, and in this chapter, we will continue to study this matter wave and also try to learn what the Schrödinger equation gives you in three different cases. First, we will study the electron behavior in an infinite potential well, which means that now the potential energy becomes infinite on both ends, so electron is confined between them. And as a second example, we will consider the case of the finite potential well. So in this case, it is similar to the infinite potential well, but the height of this potential is not really infinite. Okay, and then lastly, we will study how this electron behaves in atomic hydrogen. And this is also called the Bohr model, and it gives us the idea about how atoms exist. Okay. Before we begin, let me mention two very important principles in quantum physics. The first one is the confinement principle. Okay, you know, in this chapter, we are studying matter waves, which are anyway waves. And if you remember from what we have learned, the traveling waves can have any wavelengths, just like many sine waves shown here, right? But once you have formed a standing wave by fixing both ends of the wave, it looks like this. So for example, in the first case, if you call the distance between the two ends to be L, just like here, this distance L is actually equal to the half of the wavelength. And in the second example, the same distance corresponds to one full wavelength. And in the third example, it corresponds to 1 plus half of the wavelength, and so on. So as you can see, once you have formed a standing wave, now you can find a relationship between the wavelengths and then the distance between the two ends, just like here. So 2L, twice of L, must be equal to the wavelengths multiplied by certain integer. And this integer n is what we call a quantum number. Okay, and this kind of relationship gives you the wavelengths just like shown here. And this is basically the confinement principle, which means that once you have formed a standing wave by fixing both ends, now the wavelengths cannot be continuous numbers, but has to be discrete numbers just like shown here. This confinement principle is in fact true for both the classical standing waves and also quantum standing waves. Okay. Okay, and then the second principle I'd like to mention is the correspondence principle. Well, try to read what is written here. At large enough quantum number n, the predictions of quantum mechanics merge smoothly with those of classical physics. It sounds a little difficult, but basically what it means is that even though classical physics and quantum physics look different, they are actually not separated theories. In fact, the classical physics is simply a large world version of quantum physics, while quantum physics correctly describes the physical world down to the small size limit. So they are actually coming from the same natural laws. Okay, now given those principles, now let's try to see what happens to the electrons' matter waves when we have a special case of infinite potential well. This is a very well-known problem, and it is also called the particle in a box. Okay, so what we mean by this infinite potential well is just like this. This potential energy has to go into the Schrödinger equation, and then it is given as 0 inside the area between the 0 and L, which is just like the figure shown here. Okay, so inside the area which is between 0 and L, there is no potential, which means the potential is 0. And outside of this area, which is on the negative side of X, and also X being larger than L, the potential is actually infinite. So what it means by potential being infinite is that electrons cannot exist there. Okay, so that's why we call it a particle in a box. So electron will exist inside this box and cannot escape. Okay, so let's try to solve the Schrödinger equation in this case. And then if you remember from chapter 23, we learned that the general solution to the Schrödinger equation can be written in the exponential form like this. But we also learned that the exponential of the complex number can be changed into the sine function and also cosine function. And here, we will use this form of the sine function and cosine function instead of the exponential form because it is simply easier. Okay. And then now what we want to do is we will use this type of general solution and try to find what it will look like inside this infinite potential well. So therefore, basically, what we have to do is we have to find what this A is and what this B is, and lastly, what this K is. Okay. Now, in order to do that, let's again go back to the confinement principle. According to the confinement principle, when x is equal to 0 here, the wave function must be 0. So therefore, actually cosine function cannot become 0 there. So therefore, which means that we need to use the sine function only. So as a result, now we can conclude that b must be equal to 0. And at the same time, on the right side here, now this wave function again has to become 0 on this side due to the confinement principle. So therefore, if you insert x equals L into the equation, this also has to become 0. So therefore, from there we can conclude that k multiplied by L must be integer multiplied by pi. So from there, we get the relation that this wavelength of this any standing wave inside this infinite potential well can be written this way. Okay. And then what will be the A? In fact, we already learned that if you take the square of this wave function, it gives the probability density function. And then if you integrate this probability wave function, probability density function over the entire area, it has to become 1, right? This is also called the normalization condition. And by simply performing numerical mathematical integration, we find that A must be equal to square root of 2 divided by L. Okay. Oops. Oh. And then now finally, you can summarize that this wave function has the shape like this. So square root of 2 divided by L and sine of n pi divided by L multiplied by x. But this is only true within this range, which is actually inside this well over here. But there will be nothing over here and nothing over there. So therefore, outside of that area, the solution will become simply 0. Okay. Okay, we have just seen that the wave function of the matter wave can be written using the sine function inside the infinite potential well. And you know that some sine functions can be positive in certain area, but it can also be negative in the other area. So it is okay for wave functions to become negative. But now let's think about the probability density. Actually, it is the probability density function which actually represents the existence of these matter waves. So therefore, now probability density must be always positive. And so we calculate it by simply taking the absolute square of the wave function like this. And then so result simply becomes the square of the sine function. And then the result will look like this. The first one is the case when we have n equals 1. The second one is the case when you have n equal 2, and so on. And as you can see, if you go to very large n, for example, even higher than 15, it will look almost flat. And then it will just look like simple constant flat number, just like what we can expect from the classical physics, which is consistent with the correspondence principle. Okay, and if you look at the second case, now the probability of finding an electron in a certain area can be calculated by simply integrating this function over that area. And now if you do that in the middle of this well, now you can see that the probability of finding an electron near the center of this well becomes almost close to 0, which is quite strange result, right? So this strange result is because now we have a quantum matter wave, okay? And such a thing will not happen in classical physics, okay? And then how about total energy? Okay, now try to remember what we have learned from chapter 38. There we learned the operators that can, from which we can calculate many physical properties. From there, we also learned the total energy operator. And so the total energy operator was expressed in this way, particularly including the second derivative with position. So if you are simply taking the second derivative of the position using this solution to the matter wave, then this term comes out. And then you can finally summarize that total energy can be given in this form. Here, well, I do not expect you to memorize this because it looks a little bit complicated, right? I never expect you to memorize complicated numbers, but important thing, something that you have to remember is that the total energy now becomes proportional to the square of the quantum number, right? Okay, this much you have to remember. Okay, what we have just seen is the case of so-called one-dimensional potential because we consider the potential to exist only along the x direction. But in fact, you know, we are living in three-dimensional space, so therefore electrons also exist in three-dimensional space. So we have to consider a potential which looks like this, which is along both x direction, y direction, and also along the z direction. So in that case, now wave function must be written as a function of these three different variables, which is simply a product between the wave function along x and wave function along y, and also the wave function along z. And in that case, you can actually use this, you actually get different quantum numbers along three different directions, and x, and y, and z. So therefore, what you have to remember is that now in three dimension, the solution basically looks similar to what you have done in the one-dimensional case, but here in three dimension, you have three different quantum numbers. Okay, so as a result, when you calculate the total energy, you know, energy is just a scalar. So if you have energy along three different directions, the total energy will be simply a summation between these three numbers. So therefore, finally, this will be the final total energy that you are getting. So this is what you have seen in the previous slide in the case one-dimensional case, but here in three dimension, you have a summation between the same numbers along three different directions. Okay, but in this lecture, we will pretty much consider only the one-dimensional case. three-dimensional case is actually difficult to solve. Okay, so let's go back to the one-dimensional case. And now let's think about what is actually happening when you change energy. You know, we just learned that in the infinite potential well, the energy is actually proportional to the square of the quantum number. And then if you change the n from 1, 2, 3, 4, 5, as you can see, if you go to higher n, the distance between nearby energy levels become larger and larger, simply because the energy is proportional to the square of the quantum number. Okay, and then what it tells you is that now in this quantum physics, especially in the case of infinite potential well, the available energy levels are not continuous, but they are discrete, which is completely different from the case of classical physics. Okay, so in this case, actually, what it means is that now electron can move only between these available levels, and then let's give them some names. The state with the lowest energy, which corresponds to n equals 1, let's call it ground state. This is the state with the lowest energy, and the ground state means that just like we are standing on the ground when we are having the lowest potential energy, right? So therefore, the state with the lowest energy is called the ground state. And when you go up, all of them are called excited state. So n equals 2 is called the first excited state. It is not the second excited state, but it's the first excited state, because n equal 2 corresponds to the lowest energy state among the excited states. Okay, so therefore, the state with n equals 3 here is called the second excited state, because it is the second lowest energy state among the excited states. Okay, and then now suppose one electron originally on the second excited state moves up to the fourth excited state. You know, it actually means the total energy of this electron has been increased. And then according to the conservation of energy, this much energy cannot be created. So it has to come from somewhere. So from where can it be? Actually, what we can do is that we can send the light, actually the photon, which has exactly the same amount of energy between these two states, and then make the electron go up. So in that case, we know that now the energy has changed from E3 up to E5. So therefore, the difference of energy that electron gained is actually E5 minus E3, which is a positive number. So therefore, the photon, which has the exact amount of energy of E5 minus E3, has to come in and make the electron go up. So that photon, of course, according to the Planck's idea of light quantum, exactly must have the Planck constant multiplied by this frequency being equal to E5 minus E3. Okay, and then how about the case of electron, for example, moving from higher state to the lower state? For example, shown here. If one electron is moving from the third excited state down to the first excited state, now it is changing from E4 into E2. So therefore, the difference in energy of this electron, which is E2 minus E4, is actually negative. It means that now electron energy has been reduced. So in that case, the photon will come out according to the conservation of energy. So therefore, the photon that is coming out during this process must have the frequency which is exactly equal to E4 minus E2 divided by the Planck constant. Okay, and this process is actually called the de-excitation because it is the opposite of the excitation. Okay, so far we have studied the case of infinite potential well, but then in the next slide we will study a little bit more realistic case compared to the infinite potential well, because in reality no potential well is infinitely high. This infinity exists only in mathematics and physics. What we actually have is very large number instead of infinity. So therefore, now we have to change the potential just like this. So here, we still have the same zero potential energy in the area between 0 and L, but outside of this area, instead of infinity, we will have a certain height of potential, which is of course smaller than the infinity. And then the figure will look like this. Now this part has a certain height, which is not infinity. Okay, so in that case, now try to think about how we can solve the Schrödinger equation and then see how the matter wave come out. So the first thing we know is that, inside this area, it looks pretty much similar compared to the case of the infinite potential well. So therefore, the solution will also look similar. So therefore, we have solutions like this, which is pretty much similar to what we learned before. But then, now the boundary condition has changed. In the case of infinite potential well that we have studied before, there was the confinement principle. And because of this confinement principle, we had 0 of the wave function here and also 0 here. That is not the case anymore. The potential well is not infinite, so therefore the wave function doesn't have to be 0 here. So it can have some number in this area. So in order to do that, let's do this. Now in that area, we do have a potential. So therefore, we have to insert this potential energy in the Schrödinger equation. And then if you look at it carefully, what does it look like? Now this wave function, this differential equation looks like this. If you take the second derivative of this wave function, now it is the wave function itself multiplied by a certain number. So what kind of function should that be? And actually, this function must be the either exponential function or the sine and cosine function. Now, in that case, what do you have will depend on the sign of this part. If this is positive, then you will have the exponential function. And if this part is negative, then you will have the sine or cosine function. Now, here in this online lecture, we will only consider the case where this potential, height of this potential well is still much larger than the total energy, which means that electrons are pretty much close to the bottom of the well. And then I will leave the other case to your homework. Okay, so in that case, now we have a positive number for this part. So therefore, now let's replace that part using a certain number square, which we call gamma square, because that part has to be positive. And then now our Schrödinger equation can be very simply written this way. So therefore, in this case, the general solution for this type of differential equation can be written using the exponential form. So you have a square, so therefore solution may be exponential of plus gamma x or exponential of minus gamma x, okay? Okay, using the general solution we have seen in the previous slide, now let's try to think about the boundary condition. Now here, we do not have an infinite potential well, so therefore the confinement principle doesn't work anymore, but we still have a different type of boundary condition, which means that if you go to infinitely far away from the well, then there should be no electron. So therefore, we can write it this way. The wave function at x being approaching the infinite side has to become 0. So in order to satisfy this condition, actually the exponential of plus gamma x must disappear, because exponential of plus gamma actually means that when you go to large x, it will also become infinity instead of 0. So therefore, in this case, the solution will have this form, and this part corresponds to the right side of the finite potential well. Then how about the left side? In the case of left side, now if you go to negative infinity of x, again, there should be no electron, so therefore, solution again has to become 0. So in that case, now exponential of minus infinity has to disappear, so the solution must have the form of the exponential plus infinity. and then the shape will look like this. Okay, these are the wave functions. And like I said before, it is okay for the wave function to become negative. For example, here, this is negative, also negative. But the probability density, which is the square of this wave function, always have to become positive, and they will look like this. Now, try to compare this with the solutions that you have obtained from the case of infinite potential well. You see that between this area here, they look similar. This is almost a half wave of sine function, and this is almost one wavelength of the sine function. But in the infinite potential case, there was a confinement principle. So therefore, number has to be 0 here and also 0 here. The same thing, the 0 here and 0 here. But in the case of finite potential well, as you can see, now this wave function or the probability of the electron to exist actually penetrates into the potential well. This phenomena is called the tunneling or quantum tunneling. This phenomena does not happen in classical physics. Think about you have a baseball inside a certain box, and then baseball cannot penetrate into the wall, right? So therefore, this type of tunneling is strictly the quantum phenomena. And this happens when you have a potential well which is lower than being infinity, okay?